In 1987, a black Buick pulled up to a stoplight somewhere in Middle America, and the driver next to it was probably in a Ferrari or a Corvette or maybe a Mustang GT, and he glanced over at this boxy American family car, and he either laughed or didn't even notice, and then the light turned green, and the Buick absolutely destroyed him and drove away, and that driver spent the rest of his life wondering what just happened to him. That Buick was the Grand National, and it was making somewhere around 300 horsepower from a turbocharged V6, and it was genuinely quicker than nearly everything on the road that year. And the reason it existed, and the reason it worked the way it did, traces back through 40 years of racing history, through Indianapolis and Formula One and the Swiss Alps, and a bunch of brilliant engineers solving the same fundamental problem over and over in increasingly creative ways. That problem was this: how do you get more power out of an engine without just making the engine bigger? The answer was already sitting in the exhaust pipe the whole time. So real quick, let's talk about what a turbocharger actually is, because the basic concept is so elegant it's almost annoying that it took so long to catch on in road cars. Every internal combustion engine works by burning fuel and air together in the cylinders, and the more air and fuel you can burn per cycle, the more power you make. So one obvious approach is just build a bigger engine with bigger cylinders that can hold more air naturally, but bigger engines weigh more and cost more and drink more fuel. A turbocharger attacks the problem differently. Your exhaust gases are leaving the engine at enormous speed and temperature, and that energy is basically just wasted. Normally, it goes out the pipe and heats up the atmosphere and does nothing useful. What the turbo does is put a small turbine in that exhaust stream and spin it, using energy that was going to waste anyway. And that turbine shares a shaft with a compressor on the intake side, which forces compressed air into the engine at above atmospheric pressure. So now your cylinders are getting more air than they could ever suck in naturally, and more air means you can burn more fuel, and more fuel means more power, and you got there by harvesting waste energy. The turbine wheel in a road car turbo spins somewhere between 80,000 and 250,000 RPM, which is so fast that when the bearing system fails, it fails spectacularly. And the exhaust gases are anywhere between 800 and 900 degrees Celsius flowing through the turbine housing, which means the materials involved are basically aerospace-grade stuff, the same alloys they use in jet engines. Now, boost pressure is how you measure how much extra air the turbo is forcing in, and it's expressed as bar, or PSI, above atmospheric. Road cars in the 1970s and 80s ran maybe half a bar to 0.8 bar, which is about 7 to 12 PSI. High-performance Japanese sports cars pushed to 1.0 bar. Formula One qualifying engines in the mid-1980s ran over 4 bar, which is more than 60 psi, and the power numbers they produced were genuinely insane, but we'll get to that. The problem that makes turbocharging difficult on a road car specifically is what everyone calls turbo lag, which is the delay between when you press the throttle and when the boost actually arrives. The turbo needs exhaust gas energy to spin up, and at low RPM there isn't much of it. So you press the gas and nothing happens, and you press harder and still nothing, and then suddenly everything happens at once, and if you weren't ready for it, the car might be trying to turn left when all that power arrives, and that can go very badly, very quickly. Every interesting part of this story is basically engineers fighting turbo lag, one way or another. The technology itself goes back to 1905, when a Swiss engineer named Alfred Bucci patented the basic concept, and then materials science spent the next few decades catching up to the idea. And the real proof of concept came in World War II, when American bombers needed to maintain power at high altitude, where the air is too thin for naturally aspirated engines to function well. So GE built turbochargers for the B-17 and B-24 and the P-38 and the P-47, and they worked at industrial scale, and that was the proof. The technology survived mass production under brutal conditions. After the war, the knowledge existed, but for road cars, the timing was always wrong until the 1960s, when GM made two cars simultaneously that basically proved turbos could work in passenger cars, and also proved that the technology wasn't ready yet. The Oldsmobile Jetfire in 1962 used a Garrett turbo on a 3.5-liter V8, and to prevent the engine from destroying itself under boost, they used a water methanol injection system Oldsmobile called turbo rocket fluid, which suppressed detonation, and it worked fine as long as you kept the reservoir full. But most owners didn't bother or didn't know they needed to, and when the fluid ran out, the engine protection went with it, and most dealers just converted the cars back to normal carburetors and gave up, and Oldsmobile quietly killed the program within a couple of years. The Corvair Monza Spider did basically the same thing at basically the same time and met basically the same fate. So turbocharging vanished from American production cars for over a decade, and the industry filed it under "cool idea that doesn't work in the real world" and moved on. What actually happened next was Indianapolis Motor Speedway. The Offenhauser engine had been winning races at Indy since the 1930s, and it was a legendary piece of engineering, but by the mid-1960s, teams were looking for more power, and someone bolted a Garrett turbocharger onto the 2.75-liter Offie four-cylinder, and in 1968, Bobby Unser won the Indianapolis 500 in a turbocharged car, making 750 horsepower from 2.75 liters, and that number basically should not have been possible, and everyone saw it happen. By the mid-1970s, turbocharged Offies had won 5 consecutive Indy 500s, with engines eventually exceeding 1,000 horsepower. And this wasn't some exotic fringe experiment. This was the dominant technology at the most prestigious oval race in the world, and it kept winning for years, and the lesson was impossible to ignore. What Indianapolis proved was that turbocharged engines could survive endurance competition and make staggering power, and the people who ran road car programs at BMW and Porsche and everywhere else were paying very close attention. And then the oil crisis happened. October 1973, and OPEC cuts oil supply, and gasoline prices quadruple in a matter of months, and suddenly every automaker in the world has a problem, because their products are large displacement, naturally aspirated engines that drink fuel at rates that used to seem fine and now look completely irresponsible. The performance car was basically dying. American muscle cars were getting strangled by emissions regulations. BMW was about to release a turbocharged version of their 2000, and the timing could not have been worse. The BMW 2000 Turbo debuted at the Frankfurt Motor Show in September 1973, making 170 horsepower from a 2.0-liter four-cylinder. And for 1973, that was a genuinely impressive power density number. And BMW was so excited about it, they printed the words 2002 Turbo on the front spoiler in mirror-reversed letters so drivers ahead of you could read them in their rear-view mirrors and understand what was about to happen to them. Then OPEC hit a month later, and suddenly Germany was implementing speed limits and fuel rationing, and politicians were debating the car in the Bundestag, and BMW had to remove the provocative lettering from all production cars, and the whole thing became a PR catastrophe. They built 1,672 of them and stopped. The 2002 Turbo is Europe's first series production turbocharged car, and also one of the great examples of perfect timing meeting terrible timing simultaneously. But BMW had learned something. The M10 engine block that powered the 2002 Turbo was going to come back in a very different context. While BMW was having its motorsport meets oil crisis moment on the consumer side, Porsche was working on something more intentional and more influential. Hans Metzger was Porsche's engine genius. He'd been there since the 1950s, and by the early 1970s, he'd already designed the Flat 12 for the 917, which was producing well over 1,000 horsepower in Can-Am specification, which remains one of the most terrifying race cars ever built. And then he was asked to do something almost the opposite, take turbocharging from that extreme environment and make it work in a production road car. The 1975 Porsche 930 Turbo started with a 3.0-liter air-cooled flat six with a single KKK turbocharger and Bosch fuel injection at 6.5:1 compression, producing 260 horsepower and making 0 to 60 in about 5 seconds, which was extraordinary in 1975. And Metzger knew from the racing work that you couldn't run high compression with a turbo without risking detonation, so he dropped the ratio way down and accepted the slightly worse off-boost response as a trade-off. In 1978, Porsche enlarged the engine to 3.3 liters and did something that seems obvious in retrospect, but was genuinely innovative at the time. They added an air-to-air intercooler tucked under a restyled rear spoiler that became the car's most recognizable visual feature. The intercooler cools the compressed intake air before it enters the engine, so you get more oxygen per cylinder, and also dramatically reduces the tendency to knock, so Porsche could push boost pressure higher and make 300 horsepower. Car and Driver clocked 0 to 60 in 4.9 seconds and called it the fastest production car they'd ever tested, and Road and Track essentially described it as the car every Porsche enthusiast would do anything to own. But the 930 had a problem, and the problem had a name. People called it the Widowmaker. Here's the sequence that got people killed. You're approaching a corner and you press the throttle and nothing happens because the turbo isn't spooled yet, and you press harder because you need the power, and then the turbo delivers its full torque to the rear wheels all at once, and the rear-engined layout means enormous weight over those rear tires, which now suddenly have more force going through them than they can handle, and they break loose, and the instinctive reaction is to lift the throttle, which transfers weight forward and unloads the rear tires completely, and the car rotates on you, and there is essentially no recovering from that sequence in a 1970s 930 with no electronics and a 4-speed gearbox that leaves you in a very tall gear at the wrong moment. The 930 established turbocharging's reputation in performance cars as something dangerous and rewarding in equal measure. And that reputation wasn't wrong, it was just incomplete, because the real story was that the lag was the hazard, and every subsequent turbo development was trying to eliminate or manage it. The same year BMW killed the 2002 turbo program, a Swedish engineer named Per Gillbrand was starting a project at Saab that would approach turbocharging from a completely different angle. Saab's problem was that they needed more power but couldn't afford to develop a new engine family, and so the thinking was use a turbocharger to get 6-cylinder performance out of their existing 4-cylinder. And this wasn't about making a sports car, it was about making a practical family car that happened to be fast. Gillbrand partnered with Garrett engineer Jeff Kershaw to develop what became the T3 turbocharger, specifically for road car use. And the key insight they brought was that road car turbos needed to prioritize low-end response and reliability over peak power, because road cars spend most of their time at partial throttle at moderate RPM, not screaming around a racetrack at maximum boost. The 1978 Saab 99 Turbo made 145 horsepower from a 2.0-liter 4-cylinder at just half a bar of boost with 7.2:1 compression. And the lag was genuinely manageable compared to the 930 because the turbo was sized to spool quickly rather than to maximize peak power. But what Gillbrand did in 1982 was actually more important than the car itself. He developed something called automatic performance control, which was the world's first electronic knock-sensing boost management system. Here's how it worked. A piezoelectric sensor mounted on the engine block detected the characteristic vibration signature of detonation, which is the pre-ignition ping that destroys engines, and rather than just retarding the ignition timing, which was the conventional approach, Gillbrand's system modulated the wastegate valve to physically reduce boost pressure until the knock disappeared and then slowly brought it back up. This lets Saab raise compression from 7.2 to 1 all the way to 8.5 to 1 and later 9.0 to 1 on the 16-valve engines because the system would protect itself automatically, and higher compression means better thermal efficiency at part throttle, which means better fuel economy when you're not using the boost, which was the entire point. Car and Driver called it the most ingenious turbo controller conceived since the wastegate, and they weren't wrong. The direct descendant of what Gilbrand invented is in basically every modern turbocharged engine. Meanwhile, Formula One was about to take the turbo concept to its absolute theoretical limit and burn it to the ground. The FIA rulebook since 1966 had allowed 1.5-liter turbocharged engines as an alternative to 3-liter naturally aspirated ones, and for a decade nobody took that option because the technology wasn't there. And then, in 1977, Renault showed up at the British Grand Prix with the RS01, and nobody was worried because the thing was unreliable and slow. But the concept was right. Renault knew it was right. They kept developing. In 1979, Jean-Pierre Jabouille won the French Grand Prix in a twin-turbo Renault RS10, making around 520 horsepower from 1.5 liters, and the naturally aspirated cars were making maybe 480 to 500 from 3.0 liters, and everyone watching understood that the age of turbo in Formula One had arrived, whether they wanted it to or not. Ferrari came in with turbocharged V6s, Brabham partnered with BMW, Honda started supplying turbo engines. By 1983, every front-running team was turbocharged, and Nelson Piquet won that year's championship in a Brabham with the BMW engine. The BMW M12 engine is worth stopping on for a moment because it represents the most extreme expression of what a turbocharger can do. The block was the M10 four-cylinder production engine, the same basic design that had been in BMWs since 1961, just a humble passenger car engine displacing just under 1,500 cc, and Paul Roche's team at BMW Motorsport fitted it with a single large turbocharger and kept pushing the boost until the power numbers stopped making sense. By 1986, the qualifying version of the BMW engine was producing an estimated 1,400 horsepower from 1.5 liters from a production engine block at over 5 bars of boost pressure. Roche himself said the dynamometer maxed out at 1,280 horsepower, and the estimate of 1,400 was an engineering calculation, not a measured number, so there's some uncertainty there. But even 1,280 horsepower from a 1.5-liter four-cylinder engine is a number that doesn't feel like it should be real. The story goes that Roche preferred engine blocks that had already done 100,000 kilometers of road use because their casting integrity had been proven by actual service, and the qualifying engines were essentially grenades that would survive maybe a flying lap before they needed rebuilding. At the same time, Porsche was building the most sophisticated turbo F1 engine of the era for completely different reasons. McLaren boss Ron Dennis commissioned Porsche to design a turbo V6 engine, paid for by Mansour Ojeh's investment group, and Hans Metzger again built the thing prioritizing reliability and drivability over raw peak power, and the tag Porsche V6, making around 715 horsepower in race trim, powered Niki Lauda and Alain Prost to 3 consecutive drivers' championships from 1984 to 1986, winning 25 races from 68 starts, and Porsche only built 40 of these engines total. Then Honda arrived and ended the conversation. The 1988 McLaren Honda MP44 with Senna and Prost won 15 of 16 races, which is the most dominant F1 season ever recorded, and the FIA had seen enough. Turbos were banned from Formula One for 1989 because they'd made the racing boring. Too much power, too efficiently delivered, one every week. But 15 years of F1 turbo development had produced an enormous body of engineering knowledge about thermal management, bearing technology, intercooling, electronics, boost control, and durability under extreme conditions, and all of that knowledge was already flowing back into road car programs. Group B rallying ran from 1982 to 1986 and produced a different kind of turbo knowledge transfer through something called homologation specials, which are basically the most wonderful scam in automotive history. The rules said you needed to build 200 road-legal examples of your competition car, and manufacturers interpreted this as an invitation to put racing machines into showrooms, and the results were extraordinary and eventually fatal. Audi did the first and possibly most important one. Ferdinand Piëch pushed through a project combining a turbocharged inline-5 engine with permanent all-wheel drive in a road car, which everyone said was unnecessary and probably too heavy and complicated. And then the Audi Quattro started winning rallies in ways the rear-wheel drive competition couldn't match because all four wheels were putting the turbo power to the ground instead of two. The Sport Quattro homologation special from 1984 made 306 horsepower from a 2.1-liter 5-cylinder with over 500 horsepower in competition specification, and it was also basically undrivable for normal people, but that was the point. It existed to satisfy a rulebook requirement, not to sell to accountants. Peugeot won more championships than anyone with the 205 T16 under Jean Todd's direction, and Lancia built the Delta S4, which combined a turbocharger and a supercharger simultaneously, so there was no lag at any RPM anywhere in the power band, and it made somewhere between 480 and 560 horsepower in competition form. And then Henri Toivonen crashed his S4 at the 1986 Tour de Corse, and he and his co-driver didn't survive. And combined with spectator fatalities earlier that year at Rally Portugal, the FIA canceled Group B for 1987 because the cars had become faster than the roads and the crowds, and probably the drivers, could safely handle. But the technology survived through the production cars. The Ford Sierra RS Cosworth, with its Cosworth-built turbocharged 4-cylinder, was homologated in 5,545 units for Group A and went on to win 84.6% of races it entered across multiple touring car championships over several years, which Motorsport magazine called the most successful road-derived racing car of all time. The Lancia Delta Integrale, the direct descendant of the S4 program, won 6 consecutive World Rally Championship manufacturers' titles from 1987 to 1992, and that record still stands. All right, back to road cars and the 1980s, which is when turbos went absolutely everywhere, and some of it was brilliant. And some of it was the automotive industry discovering what happens when you put a technology into production before you fully understand it. The Renault 5 Turbo for 1980 was one of the most audacious things anyone did with a road car in that decade. Someone at Renault decided to take a small economy hatchback and completely rebuild its rear end around a mid-mounted turbocharged 1.4-liter engine and widen the bodywork to fit enormous rear tires and make a road-legal rally car. And they sold about 5,000 of them, and Jean Ragnati won the Monte Carlo Rally in one on its competitive debut. The Audi Quattro road car from 1980 to 1991 went through multiple engine evolutions, and the interesting technical progression there is how compression ratio climbed as electronic management improved. The first version ran around 7.5 to 1 compression, and the final 20-valve version ran 9.3 to 1. And that gap tells you everything about how much electronics advanced the turbo story in one decade, because you could only raise compression as fast as your engine management could protect against detonation. Ferrari's own F1 turbo program under engine chief Nicola Materazzi won Constructors' Championships in 1982 and 1983, and that knowledge fed directly into the F40 in 1987, which used twin turbochargers to make 478 horsepower and was the last car Enzo Ferrari personally approved before his death. And Ferrari then spent the next 27 years refusing to turbocharge another road car because Enzo's successor company decided naturally aspirated engines were more emotionally correct. Volvo turbocharged the 240 in 1981 and made the least likely performance car in history. They called it the Flying Brick. It was a turbocharged, boxy Swedish safety car that won the 1985 European Touring Championship and beat BMWs on racetracks. And the gap between what it looked like and what it actually did is one of the more delightful contradictions in automotive history. Chrysler turbocharged everything. They turbocharged the Dodge Daytona and the Shelby Charger and the Dodge Caravan minivan, and they did it with essentially no internal expertise. Engineer Pete Hagenbuch reportedly said they had nobody who knew much more than the basics and were basically learning as they went. The 1989 Shelby CSX VNT was actually genuinely significant as the first production gasoline car with a variable nozzle turbocharger, which theoretically could change the effective size of the turbine in real time to eliminate lag at all RPM. But the exhaust temperatures in gasoline engines were hard on the vane mechanism, and Chrysler couldn't make it durable, and the technology had to wait 15 years for Porsche to solve the materials problem. The Buick Grand National is the one that makes the least sense on paper and the most sense in hindsight. GM had a turbocharged 3.8-liter V6 program going back to the early 1980s that kept getting canceled and revived, and by 1987, the final version was making 245 officially rated horsepower with a Garrett T3 turbocharger and sequential fuel injection, which was technically sophisticated for mid-80s Detroit, and every magazine that tested it went home confused because the thing ran 0 to 60 in around 4.7 seconds, which was quicker than the Corvette and the Camaro IROC Z and everything else at the price. The GNX from 1987 was 547 cars built by ASC McLaren with a ceramic impeller hybrid turbo and a bigger intercooler and an officially rated 276 horsepower, which everyone understood was an understatement, designed so the car didn't officially embarrass the Corvette. Independent testing consistently found it was over 300 horsepower, and it was running mid-13s in the quarter mile from a car that looked like your uncle's sedan. While American manufacturers were figuring out how to put turbos in everything, Japan was quietly developing what many people consider the greatest concentration of turbocharged performance cars ever produced, and doing it under a strange, self-imposed constraint. In 1988 or 1989, depending on who you ask, the Japanese automobile manufacturers made a gentleman's agreement to rate no production car above 280 horsepower and to fit speed limiters at 180 kilometers per hour. And the stated reason was road safety, and the actual effect was an arms race that everyone officially wasn't having. Every manufacturer rated their flagship sports car at exactly 280 horsepower. Every magazine tested them and found different numbers. The whole thing was a transparent fiction, and everyone knew it was a transparent fiction, and nobody did anything about it for 15 years. The Nissan Skyline GTR R32 from 1989 officially made 280 PS from a 2.6-liter twin-turbo inline-six with twin ceramic turbine Garrett T25 turbochargers, one for every 3 cylinders, and electronically controlled all-wheel drive that would have been science fiction on a road car a decade earlier. Independent testing generally found it making somewhere between 315 and 350 plus horsepower. When Nissan went racing with the R32 in Australian touring cars, it won 29 consecutive races, and the Australians started calling it Godzilla. And that name stuck, and probably tells you more about how the car drove than any specification sheet could. The Toyota Supra from 1993 with the 2JZ GTE engine is arguably the most famously over-engineered production engine in history. It made 320 horsepower in U.S. specification from 3 liters with sequential twin turbochargers, officially rated at 280 PS in Japan from the same engine. And the design philosophy was apparently build it so strong that it cannot be destroyed and then see what happens. And what happened was that tuners discovered you could run 600 horsepower on the stock bottom end reliably and push past 1,000 horsepower with engine internals. And the legend of the 2JZ was born from that structural excess. The Mazda RX-7 FD from 1992 brought sequential turbocharging to a rotary engine, which was genuinely difficult engineering because rotary exhaust temperatures run even higher than piston engines, and the heat management challenges were severe. The sequential system had 4 control solenoids, 4 actuators, and extensive vacuum plumbing connecting everything together, and it worked brilliantly, and also required meticulous maintenance, and the cars that weren't maintained properly became expensive problems, and the used market reflected that reality. The Nissan 300ZX twin-turbo, the R32's more civilized sibling, won Motor Trend Import Car of the Year in 1990 and made Car and Driver's 10 Best list for all 7 years it was sold in the U.S., and it was genuinely one of the best all-around cars you could buy at any price in the early 1990s, and almost nobody remembers it correctly because the GTR and the Supra dominate the conversation. What killed the first turbo era wasn't engineering failure, it was cheap gasoline and the SUV boom. Fuel prices dropped through the 1990s, and American consumers discovered they could have a Suburban or an Explorer, and nobody needed a turbocharged 4-cylinder to save fuel when gas was $1 something a gallon. And insurance companies figured out that turbo cars got crashed more and started charging accordingly, and the 280 PS gentleman's agreement made Japanese sports cars feel artificially limited, and the yen got stronger, making them expensive, and one by one the great turbo sports cars got discontinued from Western markets. Honda's VTEC approach offered a different vision for what high-performance engines could look like. The B16A pulled 160 horsepower from 1.6 liters naturally aspirated and revved to 8,000 RPM with completely linear power delivery and no lag anywhere. And the NSX made 270 horsepower from a 3.0-liter V6 and demonstrated that an exceptional naturally aspirated engine in an exceptional chassis was a complete answer that didn't need a turbocharger. And Ferrari agreed with this position for 3 decades, and BMW agreed for 20 years before coming back to turbocharging in 2006. The turbo's return was forced by emissions regulations. Post-2005 fuel economy standards in the U.S. and CO2 targets in Europe made engine downsizing mandatory, and turbocharged smaller engines were the only way to hit those targets while still giving customers enough power to feel good about the purchase. The technology that came back was transformed by everything learned during the first era. Direct fuel injection let modern engines run compression ratios of 9.5 to 10.5 to 1 with turbocharging, compared to the 6.5 to 7.5 to 1 that was necessary in the early years. Electronic management systems monitored knock and adjusted boost in real time continuously at every RPM and load point. Twin-scroll turbine housings separated exhaust pulses to accelerate spool-up. Ball-bearing center sections cut rotational friction by more than half. The BMW N54 twin-turbo inline-6 from 2006 won 6 consecutive International Engine of the Year awards. Ford's EcoBoost V6 in the F-150 pickup made more power with better fuel economy than the V8 it replaced. Volkswagen's TSI engines turbocharged three-cylinder economy cars. The technology went everywhere it had tried to go in the 1980s, and this time it had 40 years of refined engineering behind it, and it worked properly. The Gentleman's Agreement in Japan dissolved between 2004 and 2005 after the association chairman stated publicly that they'd found no relationship between power output and fatality rates, and the 2007 Nissan GT-R launched at 473 horsepower, and the fiction was officially over. Here's what the whole arc means when you look at it together. The turbocharger was theoretically sound in 1905 and proven in aviation by 1945 and demonstrated at Indianapolis from 1968 onward. And the reason it took until the 1970s to appear in road cars and until the 2000s to become genuinely ubiquitous isn't that the concept was hard to grasp, it's that every piece of the supporting technology had to reach a certain level of maturity before it worked reliably and affordably in a product that needed to survive 200,000 road miles, owned by someone who didn't know or care how it worked. The electronic engine management had to be invented. The bearing systems had to be refined. The material science had to progress. The manufacturing tolerances had to tighten. The intercooler had to become standard equipment. The wastegate had to get reliable. The knock sensing had to get fast enough to react before damage occurred. Per Gilbrand at Saab put most of the pieces together for practical road cars before most of the industry understood what the pieces were. Hans Metzger bridged the racing world and the production world at Porsche twice, first with the 930 and then with the TAG Porsche F1 engine. Paul Roche at BMW pushed turbocharging to its absolute theoretical limit in Formula One and demonstrated that the technology had essentially no ceiling if you were willing to accept that the engine was disposable. The Japanese engineers at Toyota and Nissan in the late 1980s overbuilt their engines so thoroughly that those blocks are still being used to make power numbers nobody anticipated. The Buick GNX sitting at that stoplight in 1987 was the product of all of it. 40 years of aviation engineering and racing development and consumer product iteration and electronic management development and bearing research all converging in a car that looked boring and ran devastating and made the point in the most American way possible. Today, roughly half the cars sold worldwide use turbocharging. The technology is in economy cars and sports cars and pickup trucks and family SUVs, and the modern version is so refined that most drivers can't tell when the boost comes on, because there is no moment when it comes on. It's just there continuously and seamlessly, and the lag that defined the entire first era of turbo road cars is essentially gone. That's the complete story of how a device for harvesting waste energy from an exhaust stream went from a Swiss patent to an Indy winner to a Formula One weapon to a Swedish family car to a black Buick beating Ferraris at stoplights to the engine in whatever's parked outside your house right now.